Hello, everybody, and welcome back to the wonderful world of logarithms. Hopefully, you've had a chance to try the first three of our warm-up problems. You may have noticed the answer to number 3 was a little bit tricky. So if you haven't, make sure you go back and revisit those. As we continue our discussion of logarithms, how they work, and logarithmic functions, today we're going to be discussing them specifically in their context as the inverse of exponential functions. So remember we talked yesterday about the fact that both exponential and logarithmic functions relate three things. They relate a base, a product, and an exponent, right? Exponential and logarithmic functions relate base, product, and exponent. They both do. They just differ in which one they isolate and which one they emphasize, really. So it turns out that, as we saw yesterday, exponential and logarithmic functions are inverses of each other. If you have something in the exponential position and you need to get it out, you use a logarithm. If you have an exponent and you want to put it back up into the exponential position, you use exponential form. So exponential and logarithmic functions with the same base. Let's make that a huge, huge note. Star with the same base, because you know it's all about that base. As long as that's true, their bases match, then they are inverses of each other. And so what does that mean? What does it mean to be an inverse? Let's go deep back into the memory archives, do a little brainstorm here. Well, we know that inverse functions, from our studies in chapter 6, we learned that inverse functions undo each other, right? So whatever one function does, its inverse undoes it and gets you right back to the original input that you started. So we know that we use function notation. So if we have f of x and its inverse would be written f inverse of x. And remember, that's tricky. That little tiny -1 is not a -1 exponent in this context. It's just a way of saying f inverse. And so we saw that if you do f of f inverse of x, or the other direction is also true, f inverse of f of x, you just get out what you started with. You get out your original input because those two functions undo each other. Okay. So the last thing we need to refresh ourselves on, to recall, is how do you find an inverse function? So way back in chapter 6, when we first explored how to find an inverse function, we discussed the fact that the way to get an inverse is to simply swap your x's and y's. And along with your x's come your domain, and along with your y's come your set of all outputs in the range, right? So inverse functions have swapped x and y values, and along with that, their domains and ranges have swapped. So that's not new, that's just a little refresher, but we're going to now apply it to our topic of chapter 7, these kind of newer functions, exponential and logarithmic functions. So here's our first example that I'm going to write up for you. Our original function f of x is the very first exponential function we ever worked with, 2 to the x power, okay? And our job here is to find the inverse. Okay, well, step 1, swap. You already know it. We're just going to rewrite with y. Remember that f of x represents y, and we're going to swap y and x positions. Okay, so to find the inverse, instead of writing y equals 2 to the x, x and y trade places. So step 1 is to swap and say x equals 2 to the y power. And at this point, you guys, we have it. That's the inverse relationship right there. That's it. That's the inverse. But you know, it's really kind of hard to graph with y all the way up there, teeny tiny, in the exponent position. In order to really graph it effectively, we need to get y out of the exponent position and isolate it on its own. How do you do that? How do you isolate an exponent? With a logarithm. So we're going to take this relationship, identify the base, product, and exponent, and use that information to rewrite this inverse in logarithmic form so that our exponent y can be isolated. So step 2 is isolate y. And of course, this is a step you've done many times, except previously we did it with things like squaring and square rooting. And now we're doing it with exponents and logarithms. But the fundamental idea of isolating y for an inverse function is the same. So we're going to isolate y. In order to do that, we need to, you guessed it, rewrite as a log. So let's take a note of what our base is. Here, our base is 2. Our exponent is y. And our product, what happens when you multiply 2 by itself y times? You get out x. So we have now all the info we need to rewrite. I'm going to make a big box here for our final answer. What is our exponent? It's y. And that is equal to, the exponent is equal to the logarithm with a base of 2 of our product x. And that's it. Again, it's the exact same relationship as what we have right above it in purple. The difference here is that instead of having x, the product, isolated, our input, now we have y, the exponent, our output, isolated. So you can see here that in a logarithmic function, you put in a product and you get out the exponent that got you there.